Good morning, everybody, to PyCon 2015, second day, the first tutorial in the morning. The title is Descriptors and Metaclasses, and undertitled Understanding and Using Python's More Advanced Features. First of all, I would like to introduce myself a little bit, that you know who's speaking here. So I've been a Python user since 1999, that's quite a while, and I'm still very enthusiastic about Python. And since 2004, I give Python courses, Python training, and right now, I spend most of the time training Python, most of my time. There's a company called Python Academy. You see this nice logo up there, where I'm the CEO of. But I'm also involved in the community, so I've been chairing some Python conferences here and there. So I had 2 EuroSciPy conferences, 2 PyCon conferences, so that's a mistake. It's not EuroPython 2015, 2014, sorry. It's the last year's EuroPython I was a chair of. We're going to change this. And I'm also the chair of the Python Software Foundation. Okay, that's about me. I would like to know a little bit about you. So just maybe you can raise your hand how many years of Python you have, so I have a little bit of an overview what I can expect in terms of your Python knowledge. I know time is not the only measure, but just to give me some kind of a clue what your Python knowledge is. So who has less than 1 year of Python? Okay, just very few people. Less than 2? A few more? Less than 5? Okay. More than 10? Also a few. Okay, so it's a good mix, so the most of them are in the middle. So, good. Who of you is using Python 2 mainly? That's most of the people. And Python 3? Okay. And who of you has installed Python 3 in a machine? Who has Python 3 installed? So that's pretty much everybody. Because I'm going to target both Python 2 and Python 3, and of course, which is a bit of a challenge because there are some differences here. And I try to cater for both of the versions and see how things are going. Who of you has used IPython Notebook before? Okay, a few people. Because I'm going to use IPython Notebook. So what we're going to do, most of the course we will do kind of a hands-on session. So I will talk a little bit, and you will most of the time more or less type along. So I think that's a good thing, you can actually do something. And I'm going to use IPython Notebook. You don't have necessarily install IPython Notebook, but it would be nice because I use it myself, and I think it's a very good teaching tool. A lot of tutorials here, I attended the tutorials myself yesterday, and both of them used IPython Notebook extensively for the whole thing. Everybody should have a piece of paper, a printer handout, so I will use this heavily in the course. And I sent you class notes. Everybody downloaded the examples. Who did not download yet? So this would be the link. Just a minute, I give you, no, that doesn't work this way. This is a link here. If you just go there and download example files, we were going to need them later on during the course, during the tutorial. I prepared some examples that are too much to type, so please download these things. Good. Once you download it, we will have exercises also. So I make you do something, which is good, I think, so you can do something on your own for several minutes. And I also will provide solutions, but after the tutorial, not before, so you're not tempted to peep in the solutions. We have about 90 minutes, then I have about 20 minutes break, and then another 90 minutes. That's more or less the plan, so we will finish by 12:20, something like this. And also, please, the organizers asked me to give feedback, so if you use a guidebook on your mobile, just go to the tutorial, and there will be a feedback link. Alternatively, you can go to the web. This is the link. I sent the link around with class notes also, so if you go to the website of the tutorial, you should find this link, so people, they'd like you to give some feedback. Good. Let's get started. What are descriptors and metaclasses good for? They're kind of a little bit strange kind of things. You can get away without using them for a long time. They're not really totally necessary for a lot of things, but they can be pretty useful. So for a few things, they can be pretty useful. For one thing, they can prevent a lot of boilerplate code in some places. If you use them wisely, they might help you to prevent boilerplate code. And you might get some elegant solutions out of it. I think some very good application, especially for metaclasses, is exploring a code base, so looking at some things you don't know. If you have kind of a larger code base you didn't write yourself, metaclasses might be useful. I have some examples what you could do with metaclasses in this regard. Good. But very often these techniques are not the simplest solution, so you might find a simpler solution. If you have a simpler solution and it works, by all means use it. Because things can be kind of opaque, people might not understand what you're doing, so you have to weigh up. Do you want to make a very elegant solution people don't understand, or a simpler solution people understand better? Maybe, depends. And they can be overused. That could be a problem if people overuse these features, then might make things worse than better. But I want to give you some examples so you see what they can be used for and how they work. And therefore, you might be a bit better off to decide if it's used in a good way or not. So, therefore, you will learn here, hopefully, in this 3 hours, what they're all about. And just one goal could be just because you like to learn something new, and you don't have a real use case yet, which is fine. So it's always good to learn something new. But sometimes you might need them to understand frameworks and libraries. There are a few frameworks and libraries around that actually use them. And then it can be useful if something happens if you want to dig deeper. Very often, typically, if they're idle frameworks and libraries, you don't need to. They should hide everything away. But sometimes this abstraction is leaking, and then it's a good way to maybe dive in and look at them. And also, you might write better programs at some places, and I hope I can give you some hints here how to do it. First, descriptors. Descriptors is the first topic, and then we use later on metaclasses, which they have some examples. Actually, I use both. And these give you a fine-grained control over attribute access. So it's all about attribute access, so we spend a little bit of time. And you have more control, and you can to some way restrict what you can do with your program. And now, enough talking, I want to show you some code. No, this doesn't work. I have to do it like this. Okay. I created a new directory. I would recommend to you also create a directory. And actually, because I work with 2 versions, Python 3 and Python 2, I used environment. So I created an environment. So I gave you some instruction how to do this. So I have an environment for Python 3.4 and another shell for Python 2.7. And I would like to work with both of them. So you can work along. The first thing, we want to start the IPython notebook. So get a little bit infrastructure set up. So if you type IPython notebook in the directory where you would like to put the material for the course, and then the IPython notebook actually should come up. So I open a new browser window, otherwise it opens in another terminal. So now I can open the IPython notebook, and you will see the IPython notebook. The application will start here. Takes a little bit. And then you'll see this page. I'm not sure what it's doing. Maybe sometimes it tries to connect to internet to do a few things with. Why doesn't it work? And have the other shell where I also start an IPython notebook with a different version. So if you want to, you can only work with Python 2 or Python 3, the way you like it. But also, if you want to explore, you can also work with 2 versions, both versions. And I'm not sure why this is not coming up, which is not good. So I've done this many, many times, not a problem. Okay, this one works. So this is the Python 2, and I create a new notebook. So the first thing you should do, create a new notebook, and this would be a Python 2 notebook here, and this would be my Python 2. The first thing is I make everything a bit bigger so people can see, and typically, once you have the notebook running, I rename the notebook to something that makes sense. And I call it Python 2 in this case because it's Python 2, just to make sure. So I just check if the version is right, and the version is Python 2.7. So if this is an IPython notebook. If you type something in, then just type Shift Enter to execute a cell and create a new cell below, and then you see the output. It's just like an interactive prompt, but with the added feature that you can save your work. So if you work on the interactive prompt, everything will be gone after you are done, but here you have this notebook and it will be saved. And I'm not sure why this is not working. Now it works. Okay, see, I created a Python 2 notebook. This is the Python 2, and I make a new one here. This is different when I started from the other shell, which is a Python 3. So we see how it goes if we work with both versions here. And it is the same thing. I rename it to Python 3. Good. So everybody should have at least one notebook open. If you want to, you can have two. So I can switch back and forth between both of these notebooks. Let's get started. So it's a handout. The handout should be pretty comprehensive. So even if you get lost in between, you should be able to pick up with the handout, because I'm pretty much doing what's in the handout. So you should be able to redo what's in the handout. Descriptors. I said descriptors are all about attribute access. And descriptors are used in several places in Python. And one application of descriptors is properties. And I want to show you beginning properties. Properties are conceptually a bit simpler to understand. That's why we start with properties. And I'll show you how a property works. And I have actually several solutions for properties. There are several ways of doing it. So if I have a class which is square, so that's Python 3, so I wouldn't need to inherit from object, but it doesn't hurt when you do it. So if you do inherit from object, typically your code should work with Python 2 and Python 3, the same. With the same code base. So I create an init method, which is just a constructor here that takes a side, and I set the side to a value, self-side, and then I create three methods. You don't see yet what they're all about. A get, a set, and a del method. And that's typically how properties work. I call them a set here. You're typically free to call them whatever you like. And this is just a get first, a get, and then if I have a get, I just return if I have a square and have one side, I just multiply the side by itself. So I square the side. And you can do it like this, or you can do something like this. And then I have two other methods, set and del. But actually, I don't want anything here to happen. You can change this later if you like, and improve the functionality. But right now, I just give a strange message just to see what happens when you do something. Something like this. Cannot set area. That's the side. You can set the side, but not the area. And the same thing goes for del. I just override. I write del here, and I don't allow deletion. Just to make it simple. And you could raise an exception or something. In this case, I just print something. So this would be how typically a descriptor looks like, a property looks like, but we're not there yet, because now I have to say area equals property. You see, properties are built in. If you have the IPython notebook, it turns, I don't know if it's big enough, maybe a bit bigger. So if it's too big, I just turn off them of those bars here to get some more screen real estate. So I have a property now, and now the thing is, I need to provide this setter, getter, and deleter. In this order, I just go by the order here. You can also do it with keyword arguments, but we go with the order, the setter, and the deleter, and the doc string. I just provide a doc string. and you just write something that's useful. So that's a docstring. I can write it here. Doesn't fit area. This square. Yeah, something like this. This would be a property, and this should work with Python 2 and Python 3 alike. So now I have this square, and I can make an instance of the square. And now you can just access area here, and you should see the 25. So it's a computed property or computed attribute. So I just access area without the parentheses I don't call. It's not a method call, but in the background things go on. We will look at it, how descriptor work, how they do this. And there you get the result as the same thing as you would call the method a get in this example. So you can change the site. So if you change the site to something else, and then you look at it again, then you will see it changed. This works. If you try to set it, the area itself, then you will see it does not work. So if you want to change the area, then I just get the printed text we have here, no exceptions. If you implement exception with an exception. And then if you look at the area, it hasn't changed, obviously, because it's not allowed. The same thing goes if you like to delete the area, then you can delete it. Just get this message. That's what it's doing. Okay, this is a way to define a property. There's one problem here. You hide this important fact that's a property down here. So you implement a bunch of methods, and those methods actually you don't use directly, but at least you don't want to use directly. And then you hide the fact that areas is a property down here, and it's very difficult or rather difficult if you have a bigger class to find it out, because you have to search for this property and you might not see it in the beginning. Therefore, there's a solution with a decorator. So let's have a look at the solution with a decorator. So in our IPython notebook, you can just use normal shell commands. If you use ls, should even work on Windows, shouldn't be a problem. And then you see I have this directory here where I have the examples, the meta directory. So if you go in there, then you see, if you go to the property directory, then you see I have this square example. And if you don't have IPython notebook, you can just open in your editor, but I can just load it here, which is nice because I don't have to leave my environment and just load the whole thing, and we can look at the source code, what I implemented here. So again, I made this work with Python 2 and Python 3 alike. The only difference here is I have to say from future import print function. Yeah? So if you work with Python 2, so if you have this example here, then you will see if I go to Python 2 here, so I don't need this anymore, Python 2, then this still works, but you could say from future import print function just to get the functionality is the same as in Python 3, which is a thing I always do, first thing in Python 2, from future import print function. You see, if I just press the first letters and tab, then IPython notebook knows what to do. And now I implemented the print function as opposed to the print statement, which is the standard in Python 2, but now I have the Python 3 print function. In a lot of code bases, this is the most prominent thing you need to change. Not the most difficult by far, but maybe the most occurrences with a print you need to change to print function Python 3. Okay, now we have this version here, and let's look what we changed. So instead of using property as a normal function inside the class to create our property, now we use it as a decorator. Everybody familiar with decorators? So decorators are just functions that return functions in a certain way to make it work. But in general, this thing is doing nothing else. Placing this property here is doing pretty much the same as putting things here. So typically a property, you put something in, you get something new out, and most of the time, decorator, sorry, most of the time is used to change a function or a method in a certain way. And that's what we do here. We change it in a way to make it a property. Now we call it area, and we give it a docstring actually here. And this docstring will be used. And this is the first decorator. And then the second one will be strange. Then see we have 3 methods with the same name. Typically, it doesn't make any sense in Python to have a method, 2 methods with the same name, because only the last one will survive anyway, because they are stored in a dictionary. And then the second one will override the first one. But in this setup, it makes sense because we use our property decorator here. And if you want to only allow reading the property, the area, and not setting it in at all, you could stop here. But if you want to do something, in our case, you just want to print a silly message, but it doesn't matter, then you need to use a decorator, which actually it's a part of this area. So this is this area here, and then you have a setter and a deleter here. And using this kind of little bit strange-looking thing, you create the same thing as with this property up here. So this has exactly the same effect, but it's much more prominent because you put the property in front of the method. And then when you do this and you run it here, see I do the same thing. I just have this example. So I can access my area of 25, and I cannot set it and I cannot delete it. So this would be the standard to apply a property using this decorator and this 2 follow-up decorators, which are optional. So if you don't implement them, you will get a standard exception if you try to set or delete this area in this case. Good. This is pretty interesting, but still, it's kind of a bit verbose here because you implement 3 methods here, and they only act as one. Yeah, reading, getting, setting, and deleting. But actually, should be one. But you have to implement 3 methods. And I found another very interesting solution. Which makes things maybe a bit nicer. And this is the nested version. So I load the square nested version. You see, it knows about the files here. And now I have a little bit different version. This takes a bit more time to read, but once you understand, it's much nicer and easier to, or maybe looks better to implement. So actually I use a decorator here. I write a decorator, which is called nested property, which takes a function. That's the very nature of a decorator. It takes a function and returns something. So in our case, I just call the function and get the result of this function. And then I add to this names here, we'll see in a minute what it is, my documentation, and return a new property with 2 stars. Everybody familiar with the 2-star syntax? So the 2-star syntax actually unpacks a dictionary into keyword arguments. So let me give an example of this 2-star thing. So if I have this function with the 2 stars, keyword arguments, then you will see, I just print it out. It looks like this. So I can call this function with keyword arguments, and it will be converted into a dictionary. And inside the function now you can access the dictionary. That's one thing. The other thing is this thing, I use it here as a decorator and I write the string thing. So from here you don't really see yet what this is all about. We have to go in here to see how it's applied. Now I have my same square with the same init, but now I use my nested property and make this decorate this area. So this is this property, and this is area, which is in case here my function. Yeah. And you see, I will return the property somehow. I use this function in a certain way to build a property. And inside this method, I define 3 other methods. And then now in this case, they have to be called fget, fset, and fdel. So the name is mandatory. You have to call it like this. And I do the same actions as I had before. But now it's a bit nicer because now you see I have this area, and then you have the 3 nested ones. You see they belong together. As opposed to up here, they're all on the same level. So they belong together, but only by convention of the name. And here this might be nicer because you have this nested thing. And then I return locals. Locals gives you a dictionary of local variables. So again, if I have another function, function 2, and something like this. And now I just print the locals. So you see how locals look like. So if I call this function, too many. If I call this function, then you will see what locals is doing. Func2 gives you, and I have to give, of course, provide an argument. You see, now I get a dictionary with all the variables that are valid in this local namespace. And it's just a normal Python dictionary. Of course, the keys have to be strings because they have to be valid Python names for variables. Okay, once we do this, you see, now I call this function, and this locals, what does this locals contain? We're going to have a look at it. Of course, it contains the 3 different methods, and they will be returned as a dictionary. And then I apply this dictionary, what I get here. I add another one, which is a doc. So actually, I take the documentation string from this area function to add here, and this is just a normal dictionary assignment. And then I use properties with this strange double star syntax to create a property. It's quite a bit magic going on, but you don't have to re-implement this all the time. You just need to use it. Just have to write like this. And once you do it, you will see you get the same effect. You see the same output as we had before. And just to see what's happening, you can add a print here to see what locals actually gives back. Then you see it's a dictionary, and inside this dictionary you have the three entries: fdel, fset, and fget. Of course, there's no order because it's a dictionary. And you can look inside, or you can look at the help of property with a question mark in IPython notebook, shift enter. You see the help here, and it gives you this signature. So you have to provide a fget, fset, fdel, and a doc string. And that's exactly what the strange call is doing. So it's a little bit magic, but you don't have to re-implement it, and it might be nicer if when you implement a property, uses just this nested property decorator, and then it will be built this for you. And from outside, you see only the area, and these other methods are not seen from outside. They're kind of hidden because they're just local variables here inside this area. Good. Yeah.
Why don't you have self in the definition of array?
Because it's just a function. You see, I just put it as a function here, and this is just a helper. So actually, you could put this. No, you can put it outside. But the self, because what you're actually doing, you're building this in the end. So you want to build this, and this is the setter, the getter, and the deleter, and you want to put them here, and that's what I'm doing at this place. So the area is just a helper, just gives me the name, and just returns these 3 things. So that's why you don't need. Yeah, a static method. With static method, you have to provide, because this area is actually not called as from the instance here, because it's replaced with this. When you call it, it applies the decorator here, and you see what's happening here. You get the function here, and you call the function as a function. Otherwise, this would be called as a function. There's no instance here. The self is only good when useful when you have an instance. Which a self is, which will be handed in. There's no instance here. It's just used as a normal function in this place. Yeah. Good question.
Does the order of the fget and fset matters?
Not in here, because it's a dictionary. So it goes by name. If you look at this as a dictionary, you see there's no order. In Python 3, the dictionaries are randomized by default. If you might call it again, you might see a different order when you do it. So a dictionary doesn't have an order, yeah, in Python. It could, maybe, somehow, but here in Python, these dictionaries don't have order, so it doesn't matter. It goes only by name. Yes? Yes, the names are meant, you have to call it exactly. If you want to use this decorator, you have to call it like this. Otherwise, you would need to implement some name mapping somewhere. But if you want to use it this way, you have to call it these names. Yeah, you could, if you don't want it, but then you have to somehow tell it which method is what. So that would be exactly here. So you would need to do something different. But if you want to use it, you have to use these names. Good. That's properties. So properties can be very useful at many places, but descriptors are more general. Properties might have a disadvantage that you need to implement these properties in every single class you want to use. With descriptors, you can do a few other things. First, I want to show you a little bit theory, how descriptors work, and how they control attribute access to classes and instances here. Let's have a look at an example. I give you descriptors. I give you some source code for a typical data descriptor and then a non-data descriptor. So we will look at this. Yeah, we look at this terminology here. So this would be a data descriptor. So this is a strange kind of class. We will see in a minute what we're going to do with it because it's very different from other classes. But that's what you call a data descriptor because this is just a class. And this class has to have this get and set method, these two underscores. There are special methods, so you might be familiar with the concept of special methods in Python. Those names with a pattern, two leading and two trailing underscores, you should never make up yourself because they are reserved for special method inside Python. And newer versions of Python regularly add new special methods, like Python 3. For metaclasses, adds a prepare and stuff like this. So if you make some up, you might get into trouble. So the documentation is explicit, don't use this pattern for your own names. Sometimes you will see it, like IPython is doing something like this, but typically they use some special kind of name, but in general you shouldn't come up with. So we write this class, which is very different because it's not actually used as a typical class as you used to, making instances, but in a different context. So it's just a normal class. Again, inheriting object is optional in Python 3 and Python 2 you have to, because all these descriptors only work with new style classes. We're going to look at this. So in Python 2, there's a thing called old style classes, and you should never ever use old style classes in Python 2. They are common in Python 3. So they are very old. They are more than 10 years in the past, so never use them. And the way to get new style classes in Python 2 is using object, inherit from object. In Python 3, it doesn't hurt. So if you do it, typically you make a source code run with Python 2 and Python 3. So I'm hammering a bit on the Python 2, Python 3 thing, but I think it's important. Every new code you write, even if it's for Python 2, I think nowadays you have the option to make it work with Python 3. So make it work with both, so you save you a lot of work later when you need to port. And this is a simple thing. So inherit from object. And again, I have an init here. We will see in a minute how we can use it. And I have this getter, setter, and deleter again. And they have to be named like this. A get with two underscores, leading and trailing. And I get a self, and I get an instance in the class. So it's very different. So this signature is fixed. So you have to use the signature instance in the class. We'll see in a minute what it is. And the only thing we do here, we just print a message that something goes on and return value, our self value. And the setter gets an instance and a value, and you can set something. And here I try, I'm just very positive, I try to convert my value into upper, so assuming probably something like a string that has an upper method. If it has one, it's fine. If I get an attribute error, meaning there's no upper, I just set the plain value. That's what my descriptor is doing. And delete, I just print a message that I cannot delete it. So if I have this one, so you actually have to execute a cell. When you load it in the notebook, the cell is not executed yet. Only when you see the number here, it's executed. Yeah, you might have noticed all the things are numbered. Yeah, see, there's a 31. There's no 32 because if I rerun it, if I go in here and press Shift Enter again, now it's 34. Yeah, there are cells that are not visible anymore because if I rerun it, it will send a message to this IPython interpreter, which is running on the command line, and increments this number. So. Okay, once you execute it, now you have this descriptor, and now we can use it in a way, and I'll show you how to do it, because typically you cannot use it on your own, but rather use it in the class. So I have a class A, which inherits from object. You just do pretty much what's there. And now the typical way to use a descriptor is making a class attribute, creating a class attribute, and now use our data descriptor. Since we execute the cell, the data descriptor is available, and this data descriptor doesn't necessarily in the init doesn't take anything. It's just sets the value like this. And now I have this instance of my data descriptor here, and I can make an instance of my class. You see? And now, if you look at the class, you can access. And now you see when I access attribute, you know, when you access an attribute at an instance, and it's not in the instance, it looks at the class, and that's what it's doing here, and finds attribute there. And you see, it doesn't give me instance of data descriptor, but rather it calls, obviously, this get method at this place. So what happens? When I do this, what happens? So the first thing happens, first you use type of A, and type of A gives you your class A. That's your class. Then, pretty much you look inside the dictionary, dict. So it's a special built-in method, so dict, which gives you the namespace, all the attributes here. And then I now use attribute as a string, which gives you this data descriptor. You see, now we have the data descriptor. When you say a dot attribute, it doesn't show you this one because it's not finished yet. It's calling the get. It's calling this get method here, and now uses the instance here and the class. And the class, you can get by using the type of A, and if you do something like this, you get the same. So this kind of innocent-looking a.attr causes this kind of complicated lookup. But now you can customize what happens when people do this lookup. Yeah. So as I had this many years ago, I gave a course in Munich in Germany, and this guy said, this Python is just one big dictionary. And he's pretty right. So every time you work with names, when you do attribute access, there are some dictionary lookups somewhere. You see dict here, some dictionary kind of, sometimes there are special dictionaries, but still you do some kind of dictionary lookup and you look things up in different dictionaries to get where you want to go. So you can also access the attribute from the class. So instead of accessing it from the instance, you can access it from the class. This would give you the same effect at this place. And this would be equivalent here again. Now you have the class, you don't have to do the type thing. Equivalent using dict. And here using attribute. And then the get. And since there's no instance, you have to provide none for the instance. So you put in the none for the instance and your class. So I use a different class name here just to see. And this gives you the same effect. So it's doing pretty much the same thing as up here, but this you don't need to have type because you have the class already. And there's no instance, and if you don't have an instance and call it as none, then you get it called at the class level. So that's pretty much how it works. A few things about this strange dict thing. This dict, you see, it's a mapping proxy. It's not a real dictionary, so you can access it just like a dictionary. You can access it like a dictionary, but you cannot assign to it. So I can do something like this, and I will get this back. But if I want to try to assign to this, then I get an error message because it's a read-only thing. So, which is a good thing, so you cannot just mess around too much with it. You can access it here, and sometimes you might need to go to the dictionary in certain places. Typically not, but if you override some special methods, you might need to go to the dictionary here and there, but you cannot assign to it. Good. This doesn't work, but if I say a dot attribute and I assign it to something else, you see now my data descriptor is called. See up here? I call this set, and I get the instance here, and my data descriptor is called, and now I can set the value, and it will be set, and if you look at the value is So nothing special yet. So you wouldn't need a descriptor because it's just normally how it works. But if I set my attribute to something like this, now accessing it would give me everything uppercased, because now I trigger my set here at this place. You see, I trigger this here, and I get the value, which does have an upper method, and I will just convert it to upper. So now we have pretty strong control what happens if somebody sets attribute. You could do all kind of things here in there. And that's typically what descriptors are used for. We will see a few examples what you can make out of it. It's just, I have to give a little bit theory here, how it works, so you don't have to remember all this long lookup all the time. It's just if something goes wrong, it is good to know. You might want to look inside the dictionary and fiddle around with it. But in a typical case, you don't have to remember this whole thing because it's just working in the background. But it can be useful. Yeah.
The thing you said about the dict
Yeah.
attribute being a mapping proxy.
Yeah.
Is that only for Python 3?
No, it's in Python 2 the same. You should
I
be.
said it on Python 2 just now, and it said it was type dict.
Yeah, but did you try to assign?
No.
It doesn't. It might be a different kind of name for the object, but if you assign, a lot of things have changed underneath about dictionaries. But if you assign, it shouldn't allow you to assign. So if you do this with Python 2 and try to assign, it should give an error message. Just assign something to the attribute or to the dict, and then it should not allow to you. I don't think it has changed. You're using Python 2.7, yeah. So, but I don't think it has changed for. Always been like this with new style classes. Did you try? Not yet. Okay. Good. Okay, that's something you can do. Yeah. It did not assign. So it's the same thing. It did assign?
Did not throw an exception.
Well, I have to try it out. It should. So if I have a class in Python 2, I thought this would be, and I have a dict, and I want to assign something. Oh, I thought. Oh, it does. Okay, sorry.
Subclass an object, then it doesn't.
Yeah, this is an old style class. And if I do a new style class, as I said, see, I have to do what I preach, it doesn't work. So, yeah, sure. It shouldn't a dict proxy. It's a dict proxy, you see. Maybe we can check the break, but it shouldn't allow it because it would be very strange to allow this. Hasn't changed. It's maybe a different name called dict proxy, another called mapping proxy, but I don't think it's a big issue. Has the same effect, practical effect for usage. Okay, so let's have a look a little bit of how these things work. So you cannot assign here, but this only works when I go with the attribute. So if I look at the dictionary of the instance, so we have now to distinguish between the instance and the class. So if I look at this dict of the instance, it's empty because the attribute is not stored in here. When I assign to attribute, it won't be signed in here because it's a descriptor. On the other hand, if I have another attribute, then now I can look at the dictionary, and now you see this will be assigned in the dictionary. So if it's not a descriptor, typically when you assign, it will go to the instance. So this means self. Yeah, it's a self, because now I assign it to self, to the instance. On the other hand, when it's a descriptor, it will be stored in here and not in the instance. This has some implications we will see in a minute, because that if you're not aware of it, you might have some strange effects. So you can have a non-data descriptor, and a non-data descriptor is pretty much the same. The only thing you don't want to have you don't want to have the set method. So if I take the set method away, then it's a non-data descriptor in this case. And non-data descriptors, they have some non-data descriptors. And the del actually is not needed, so you can delete it also. The del doesn't matter in this case. The only thing, if there's no set, it's a non-data descriptor. A non-data descriptor are a little bit different. So if I use my non-data descriptor, and I set my attribute here, it's the same way as we did with this data descriptor, then things are a little bit different. So I have this here. And so I overrode it here to see something. Here, I didn't do the print. Or I can keep the print, but I return value plus 10 for some reason, just to see something is happening. And now I can make an instance here of my B. It's B now. And then if I access the attribute, you see now it gives me this self 0 plus 10 at this place back just for one reason. But now if you look in the, if I assign to it, it will be different. That's a difference. So if you look at the dictionary right now, it's still empty. But if I assign to my attribute, then so no, there's no setter in this place, and now it will be 100. And also, if you look at the dictionary, you will see the dictionary will have it. So that's a difference. Compare this to our data descriptor. If it's a data descriptor, setting will call this method, and it won't be stored in the instance. If it's a non-data descriptor, only the get will be active, and setting will actually do the normal thing. So that's a difference. It's only in the handout, I think. I don't have a. Do I have it? No, it's not. It's not. There's no code, but it's just a few lines in the handout. That's a code for the non-data descriptor. Good. So this is how this works. And there are two more things I would like to show you. Are you familiar with the two special methods? Get attribute and get attr actually, and get attribute. So those two are two special methods, and they are called at different places. So if you have an object and you access an attribute, so if you have a class and somebody accesses an attribute that doesn't exist, then Python will call the get attribute method, the get attr method, this one. That means you can implement things. If something missing, you can do something. As opposed to get attribute is always called, no matter. So if you implement get attribute, none of your attributes will be accessible in the normal way. Get attribute will be called first. So you have to be very careful, because if you override get attribute, and inside you say self dot, then it will call get attribute again, and you will get a recursion. So this has some implications, because get attribute is very strong. It always will be the first thing. So you can actually use it. This will give me an error. So I just have an example here to see when get attribute is there, you can override even descriptors in this place. Okay, I have this class here, which inherits from object, and now I use my data descriptor. Data descriptor, make an instance. And now I define this get attribute. So the long one, get attribute, which is a strong one. If I have a get attr, it wouldn't matter, because the attribute would be defined. But here I define it. Typically it's self name, so it's like you get a name as a string, and this would catch pretty much everything, because now you can do anything, and even descriptors will be overwritten. So it's important if there's a method like this. So I make an instance here of this class, and I try to access my attribute, so it even doesn't work, so it gives you no way. Even though they have a data descriptor, which would be the first thing that would be active, the get attribute is even stronger and will be called even earlier, and you do everything what you're doing here. So if you're in here, so if you try to do something like this, it's not going to work. As soon as the self dot is calling get attribute again, and then this get attribute is calling self dot again, and you have a recursion. If you try this, you will get a recursion error. So don't try this here. So you have to find other ways doing it. Typically, you call the method on the class directly to get away and don't have this self. We'll have an example later on where this is important, I think, somewhere. Good. This is something about this get attribute, which is interesting to know. When you see the get attribute, then it's very strong. So it's not directly a descriptor, but it's related to the topic because it has to do with attribute access, what's happening here. Good. One more thing I would like to show you, where you see where descriptors are at work. So it's more a little bit like a thing of curiosity, and then we dive into a few examples that can be very interesting what you actually can do with descriptors. The first thing, we define a class. This doesn't do anything. A function. We define a class, and the class is just there, the pass. And now, this function has a get method because functions are non-data descriptors. Doesn't tell us much, but it has implications because this is how Python works and how it finds so-called bound methods. Now, if you write a class, then you just define normal functions inside the class, and then these methods first belong to the class. So if I have a class C, which inherits from object, and inside I just have a method. Again, doesn't do anything, it's just here reduced that it exists. And now I can make an instance of this class, and I can access this method. And this is equivalent, so you see that's a bound method. The bound method belongs to the class C, but it's bound to the instance lowercase c. And you can also access this method through the class itself, and then it's not bound, it's just a function. So in Python 3 it's a function. In Python 2 it's called a unbound method. So if you do the same thing in Python 2, I just switch quickly over to Python 2, and I say C dot method, then it's named a bit differently. It's an unbound method, and here in Python 3 it's a function. It's a small detail. Essentially, the practical thing is pretty much the same. There's no big difference in practical usage here. So, but what happens when you want to get a bound method? Actually, to get the same thing as this one, again, you do this type. So it might look familiar. Type gives you the class. On this class, you call this, you go to the dictionary. It's the same thing. Remember, we had this long thing before. You go to the dictionary, you get the function name, or the method name in this case, which gives you this function. So, but it's not bound yet. But then you call the get. You call the get on it, and this get binds it. So that's how it works in the background. It's not too useful, admittedly, but it's interesting because it's an application how those descriptors work inside Python. So I put the instance inside and the class again, maybe through a type. And if I do everything, I get the same thing as before. So this short thing actually in the background is doing something like this. It might be a bit different, but essentially that's what happens in the background, and you get these bound methods and these descriptors at work. So actually, as soon as you write a class and use a method, you use descriptors all over the place. but you don't have to bother too much. It's just maybe very interesting how this works. Okay, this is theory. Let's look at a few examples. Hopefully, these examples make things a bit clearer. What you could do with descriptors. So I have a few examples here. So if I'm in a directory for descriptors, and first I want to make you aware of the fact that things are stored in the class. What does it mean? Let's look at the class storage. So I have this example here. Again, I have a very simple descriptor, which says it's called descriptor class storage, inherits from an object, has a default, which you don't have to supply if you don't want to, which is none. And then you have this, again, instance in the class, or owner, I call it here, set the value and get the value. Nothing special. There's no real action going on here. But I would like to show you what happens if you make several instances. If you do something like this. And then I make one class, which uses this descriptor, but I make 2 instances. That's the main important thing, 2 instances. Then you can look at the output, and then I change the attribute here of 1 instance, and then I'd look at this thing again. So it's just some printouts. And you see, I have this 2 instances, and the first time the value is 10, because I supplied the 10 here as a default value. And then I change only the attribute for class store, instance store 1. But store 2 changes also. Because if you implement it like this, then when I say attribute, it just looks up the attribute, not in the instance, as we've seen, the instance dictionary is still empty, but goes to this descriptor and gets, there's only 1 value here. And if you change it with 1 class, it will be changed the other. If you want this, that's fine. If not, then you have to be aware of this effect. Yeah? Because this descriptor belongs to the class, not to the instance. That's a big difference. So if you want to use descriptors, if you see a few more examples what they can do, then you have to be careful where you store your value. Otherwise, you might get some unintended changes. So if you only test your code with 1 instance, you might never notice. Yeah? You might get a full test coverage just making 1 instance, but you have to make a 2nd instance to see what's happening actually. So it's kind of pitfalls. And it depends. Maybe you have a example. It always works because it's not a problem, and then you run your program in a different context, and then you see the problem. So that's something to be aware of when you do this. One solution would be not storing things in the descriptor, but actually storing the value in a different way, in a dictionary. So there are different ways of doing it. You could actually store it in the instance, but I decided here to use a dictionary to store things in the descriptor. So I load it, and it's called weak dictionary storage, weak key dictionary storage. So it's essentially the same example, it's the same behavior, with one difference here. I create a hidden dictionary here which now stores references to instances. That's a little bit difficult to read here. It doesn't let me make it wider. That's how it works. I just show you what I'm doing here. I have to do it back, otherwise I get a syntax error here. So the get, actually I have this dictionary, and I have to use a special kind of dictionary, because if you use a normal dictionary, you will create a reference to an instance. When you delete the instance, the reference will stay awake, and you might get some memory problem if you create a lot of instances. So I use it kind of, let's take it just as it works like a normal dictionary, only it doesn't create references. That's all it does. It comes from the standard library, from VKRF module, and it's just good practice to use it because you won't get problems with unreachable or unusable instances stored in there. And then we just, when I access it, I use a get. The get is just a normal dictionary get method, and I return my instance. If it doesn't exist, I return a default value. And setting is the same thing. Setting now, I set the value, which I get here, and I use the instance as a key. So instances are hashable, so they can be used as keys, so I use it as a key. And once I survived all these things, I have to undo these changes, see this change at least. Then I can do the same thing as bit before. This is exactly the same code as before. You see, I make 2 instances here, and change the attribute of only one of the instances. And then I look at it. And then I can delete when you see, look, later on I delete to see what's happening in this hidden one. So if look at it now, so we have our 2 instances, both have the value 10. And I'm setting only the one for store 1, which changes to 100, but the store 2 doesn't change. This is important because now I store actually a dictionary. Yeah, there's a dictionary here, and the dictionary is in the descriptor. And for every instance, I'm creating a new key here, key value pair, where I use the instance itself as a key, and the value as a value. And then when I retrieve it, I put in the instance, and I use get. Everybody familiar with get? Yeah. So that means I try to access the key instance, and if it fails, I return the default. And this way, you can store it here. And if you look inside, you see here a generator. It's a generator, so I have to convert it to a list to see. It's a little bit wide, everything. So I convert this to a list so you can see it, because the generator isn't very useful. Probably didn't test it with Python 3. So, and now you see here it still contains, this is a key, this is the instance, and the value is 100, and when I delete it, it's gone. Because I deleted I didn't delete it from the dictionary, but I deleted the instance here. If you use a normal dictionary, you can try using normal dictionary. So just copy the whole thing and use a normal dictionary. So instead of weak dict key storage, you just call it dict storage. Yeah? And here, you just use a normal dictionary, which is supposed to be this one. And now I make an instance here of this dict storage, and you should see a difference. Whoops. Yeah. I have to print out dict storage. So I have to change everything, not only the ones. So. And now, what happened? That's probably an artifact of. Yeah. So I see. I have to change it all over the place. So if this maybe, I don't know if you can do search here and these things. Someplace I did something wrong. Finally, you see it, and it's still there, and the other one is deleted automatically because I just delete the instance, but I don't actually go to the dictionary. But since I don't create a new reference, this is vgraph dict. This will be deleted. Yeah.
So when I ran this the first time, the output that I got from div both times was a generator object items.
Yeah, because that's Python 3, and in very many places, I think I tested with Python 2 only. In many places, you get a list. In Python 2, you get a generator. Just convert to a list. That's what I'm doing here. See, I just converted to a list. Yeah, please convert. Just a question to see it, because Python 3 is very good at using either generators, iterators, or view items in one way or the other to save memory. Very often you don't need the whole object, you need only one at a time, and it can be much more energy preserving, memory preserving when you use something like a generator. Yeah, but you can always convert to a list, which is no problem for our small one. But if it has many millions of items, you don't want to convert to a list unnecessarily. That's why you get it. Hmm? Yeah.
Wouldn't you just write it so you look up the class versus parse the class out inside your method? In the getters and setters, where you got the class name there?
Yes, you could. So you could, yeah. Add hard typed it here, which is nice. This would be the class. I could use this, but here you have to go to the type, and because you only get the instance here. So you would need a type of instance to get the class. I have to think through how it works if you do inheritance and stuff. So if you do inheritance and you inherit from something, it's a descriptor. Then you might not get this one, you might get something else. I have to think through. So I haven't thought through, but something in this case, hardwiring is, I think, it's what I wanted here. The thing is, if I rename it, I have to rename everything. Yeah. Yeah, but it's very explicit that I know about it. If you use owner, no, I don't get it, because here it's would have to go to self. You see the self, because that's wrong. This is a class. This is a store. This is this class down here. Yeah, and the self would give me the instance of descriptor, and I could go to type self to get it. But if somebody does inheritance, then I might have a problem because it's hidden. Yeah, so you have to think through. So it's not that easy. So you can reason about it. The best thing, you write some tests and check what's happening. What do you want to do? So it's a little bit, because as another class is used in different context as you use normal classes, and there might be a few things. I had it obvious, so obvious, but then you write an example, you see it's a bit different. So I have to think down now, write some examples, do some tests to give you a very definite answer here. So I had it many times that I tripped over those things. That's what would be very obvious, but it was not. So maybe somebody has a time to try this out. But hardwiring is, if you rename it, you have to rename everything here. But down here, this is just debug code anyway, to see what's happening. Good. That's something you have to be aware of when you store something, that it's stored in the class, but you can go through and do something. Now I have another use case, actually, which can be useful, and I use this class storage to do attribute checking. So there are several use cases out there, but I have one here that I have this checked. I load the checked, and I show you what I'm doing here, actually. Okay, so I implement actually the same thing with the weak key dictionary we just saw before, but with a different purpose. So let's go through. What's different here? We define an optional checker, and we had a default before. The checker actually is supposed to be a function that is doing some type checking for us. Typically in Python, you don't do type checking. But sometimes, especially if you have to communicate with the outside world, then you might need to make sure that the types you get or you send out are correct before you do something. It's usually better than getting exception in Python and getting some kind of strange error from outside. So if you work with some database or something, then you might have to make sure the type is correct. So, and that's what I'm doing here. I just use my checker here. So if there's a checker is provided, then I call my checker. So if it's not callable, we get an exception, because I call it as a function and do the check. And I set my checker here. And the same thing here, this is just the hidden thing we just use a get. But here, when I say it's a set, I check that the value I get here has some special, is something special. We don't know yet, because we don't know what checker is. So checker will be supplied later. So the checker is some function that's doing some kind of checking, and if something goes wrong, it throws an exception. The rest is the same as we had before. See, now we can write now our own checking function, and this is a very simple checking function. It just checks that the value we get is an integer. So this is something you as an application programmer provide, and said, okay, I want to have it to be an integer. You could also change it. This could be integer between 0 and 100 or something. You could write any kind of check you like here. And then you use this method, which raises an error if it's not to your liking here. And then you can provide this checker here. You see now we have this restricted class with 2 attributes. And I use my isInt checker here. And I provide defaults. And then you see this wouldn't be possible here. That's why I put in the try except clause, otherwise you get an exception right away. If I use my isInt checker but use a default of 12.5, I cannot even define this class here, because the minute I define this class here, because this attribute will be set through here, and then when I create this descriptor at this place, it says, okay, this doesn't work because 12.5 is a floating point, and this int doesn't like floating points, because I check it here. Okay, So this is typically what you would write. So you write your own checker. You check it for whatever you want to check. And then you write the class. It uses some attributes. And here, you can even use it here. And here, this works because I said it default 12. This is no problem. And the same thing down here. Now, I make an instance of my class finally. And I can show you my attribute 1. And I can set it, which works. But if I want to set it to a floating point, which is not allowed, because when I do this setter is called, and the value will be in here, and then my checker will be invoked, which I supply later. This int. And then it gives me an error message and throws an error, and I cannot set it. So just we execute it first and see what happens. You see, I get this message here, this place, this exception here, because my isInt function I defined doesn't allow it and throws a value error here, throws this value error, which I catch and show the message. And the same thing here, when I try to set this attribute 1, which is supposed to be in int, to a float, I get an error message. That is something you can do with descriptors. You can write, so this is descriptor, you don't have to change this one. This would be always like this, but you can define your own functions that do any kind of checking. So it's not actually restricted to type checking. You can check anything, sizes. Yeah, you can say, oh, I don't want this value in the morning or in the evening. You can check everything. There's no problem, and you show an exception, for instance. And this is pretty, because you see now I can reuse this check thing again and again and again, setting those attributes, and you have to provide this logic only once. Certainly, you could write this logic in a different way. That's possible. Yeah, you can write a checker function and just call a checker function on a property, for instance, but we would need to call it again and again. And here it would be a bit more convenient because you can use this check class, which can you have all the logic in one place, and you don't have to duplicate logic potentially or repeat code again and again. And this is pretty declarative. And typically, if you have something more or less declarative, you just declare what you want. It's better than repeating logic again and again, maybe. So this would be one advantage. You can use a descriptor and get actually something done. Good. So when to use descriptors, when to use properties, you see you can use properties, but you will find some places where this a real descriptor, so properties are application of descriptors already, might be more useful, especially in this example, because you can reuse code more nicely than using a property. So you don't have to put property all over the place and potentially re-implement some functionality, but rather reuse it here, and you have some kind of checking. So this is a typical example. So you want to read or write something from outside, and you want to make sure something has some kind of behavior or something, then you could use something like this, and then the usage would be easier, and a lot of things would be hidden. Good. Any questions so far? Good. No questions. You have to do exercises. On page 17, exercise 1.8. So please write a few descriptors. So I will walk around. If you have any questions, you can ask me. I just turn off the mic for now. And we will be back in let's say we have 10 minutes, and then show the solutions. Okay. So who has some solutions? Yeah. So I'm going to show you my solutions, what I have. There can also always be different solutions. There are different ways of doing it, for sure. But I have some solutions I'm going to show you. Then we have a break, because the metaclass part is also interesting and quite a few things to do. Okay, I have solution. I will give you solutions. I upload them. I sent you the links or the link already in the class notes, but I will actually put the file there. So this is my solutions. You can have a different solution. So you have I saw many of you using my checker here, but actually I wrote their own descriptor. There are different ways of working. So, but if you start from scratch and don't have a checker, you can write something like this. You see, it's just a normal descriptor, and there's nothing special about the get, but the set, and the set is just checking. So we have to be careful here. Sometimes in Python 2, this would work. In Python 3, you're safe. From Python 2, something like this. In Python 2, you can compare strings and integers, which doesn't make any sense, but in Python 2 it still works, so you have to be careful. In Python 3, we will have the problem. So, but if you use apps, the value typically only works for numbers, so you have to make sure, as a side effect, it's a number. And if the absolute value is not the same as value, typically it's not positive. That's my take here. You might come with a different solution, just checking if it's not negative. It's not that simple. And I set the value. And then you just use this descriptor here. You could also use a property to do this if you want to, but descriptor would be useful, and you can use it again and again, and it would only allow positive values. So several solutions use a checker, which is fine, because once you have the checker, you can also use a small function that checks the numbers positive. That would also be possible. And if I do this, then you should see here, and down here you get, if I set something like this, you get an error message. Yeah, here already you get an error message. If I comment this out, you get a next error message. And it tells you this doesn't work here. It doesn't like. And if you do like this, everything works. So this would be one application here. Let's look at the exercise 2, what I wrote there. Yeah, so here now I extended it here, and just now I override the getter and I round the number to 2 digits. So of course it's still a float if it's rounded here, but it will only have up to 2 digits of precision here. Just as an example. So you can also do something as a getter. You see, and if I do something like this, if I have a number that's long like this, and I run my test, it will shorten it to 57, because I rounded with my rounding function to 2 digits in this place. Yeah? Here now I just override the get at this place, not the set. You could also do this in the setter and set it right here and just return the value. That's fine. It depends what you do in between with the value. This would be one way of doing it. Exercise 3. Exercise 3. Yeah. The deletion, of course, you don't have to do anything special, but you can just, if you want to give user a message, there won't be an exception here, you get a message, or do something else. So if you have some special need, you just override delete, and that's simple, and you get this message and it stays there. So if it makes sense, it depends on the application you have later. Okay, the next one is a bit bigger. You might not have gotten there yet, but let's have exercise 4. And here I implement, in Europe we have the sales tax called value-added tax, VAT. And they're different in every country. Actually, there are different rates in one country anyway also. And I just have this, now I have this total as a descriptor. Here's a total price, which takes a rate of this is in Germany is 19%, other countries have different rates. So you have a rate of at 19% on top of the net price, it would be the total price. And here, when I return it, I just say, okay, I take the net price from the instance. I fetch it from the instance, because I have the instance here. And multiplied by the rate and rounded the 2 in this case. And I don't allow setting it. So I override it here, so setting cannot be done. It's different. If you don't supply it, people can still set it in the dictionary, in the instance. If you implement it and raise and not implement error, there's no way to set it. It's different. And now I can make different classes, you see. I just have 3 classes for 3 countries, Germany, Denmark, and Luxembourg, with different rates, 19%, 25%, and 17%. And then I set a net in all of them. And when I test it here, then you see they have, when I access, I make an instance with 110 euros in this case, in all these countries. And when I access the total of all these different countries, I get a different total because I have a different rate. Yeah, this could be something can be useful. So you have the same thing again. You might want to think this looks like also a little bit boilerplate. It's the same thing all over the place to make this even shorter, but maybe that's explicit enough. So we have this. We could inherit from one class and don't implement the init all over the place if you wanted to. This would also be possible. And then just set the total in all of them. That would be maybe a bit nicer. But just I want to stress on this thing, so you can set, and you see now when you access it, things change. You can also implement it with properties, would be possible, but here I can reuse the total and just have this kind of declarative thing here, and you can define the percentage. Okay. I think it's exactly time, so for a break. Yeah. Yeah, the example 3 is just returning rounded to the digits. Any questions? I didn't ask no questions. Yeah. Yeah. So this is just a normal instance and would be exactly the same. If you set a different name, there wouldn't be a problem. They would just create a new instance in the dictionary. But if you use the same name, we can try this. It should go to the descriptor and would probably cause a recursion. If you go to the descriptor again and do this again and do this again, you can try it out. I don't want to do a notebook; it's going to block my notebook. But it should cause it because it's just an instance and it doesn't really know that's inside a descriptor somewhere. It's just the normal process. This long thing with doing the lookup stuff would happen here, and then when you do this, so if you actually try to set an attribute here with the same name as you have right now, then it should trigger a recursion. But as I said, I would need to try this out, but I'm pretty sure there should be some problem. Sometimes, if you do something like this, you might get some strange effects because you cannot think through all the possibilities very often. It happened to me. But it's just a normal instance, and there shouldn't be anything different than just going to the descriptor again. Any more questions? Yeah. I said what? No, I upload the solutions after the tutorial. So I give you all these solutions plus the solutions for the metaclasses and one zip file. It's there ready, and as soon as I'm done up. But I sent you the link already, which doesn't work yet. But in the class notes, the link is there. So let's say it's a still broken link. So I updated. Yeah. Yeah. So the link for the exercises. You mean this link? That's a link for the. Good. Any more questions? Of course, we have quite a few. The meta class is part a bit bigger, so I would like to make a break now. 20 minutes. Please be here back here about in 20 minutes, so we can start on time and we can cover all the metaclasses. There should be some refreshments and maybe something to eat outside. Yeah. So you hope you got something in the break, something to drink, some refreshments. Let's continue with the next topic, metaclasses, which is also not the simplest one, but it says advanced features here. We will see our descriptors again in one of the examples, but let's go to metaclasses. The metaclasses, I switched to Python 2 to show a few things, how things come about. So if you're in Python 2, I told you if I have a class and I inherit from object, then I get a new style class. I call it new. So just to set the things where meta classes are come from or what they're good for, you have this new style class here. So if I look at this, it says, if I look at the type, then I see the type of this class is a new style class. So that's what you always want to use. If you don't inherit from class, then you get an old style class. And if you look at it, you have this one. And if you have an old style class, then descriptors don't work, and our meta classes don't work. So if you have a meta class, you always have a new style class. So what are meta classes actually used for? I have a few. I have a slide somewhere. So meta classes, actually, conceptually, it's simple. A meta class relates to a class like a class to an instance. So if you just understand this one, there's nothing special in terms of syntax and stuff. That's different between the relation between the class and the instance and the meta class and the class. That's why it's called meta class, because it's a class of a class. And they are in the business in a different place. They let you control what happens when you define a class. Typically, when you have a class, then you make an instance, and then things happen. Here, you are in an earlier stage. You have a meta class. We're going to look at how a meta class looks like in a minute. And when you define a class, the meta class is active already. So at definition time, so to speak, the meta class is doing something, which gives you some totally different leverage what you can do. And they can be pretty useful, like object relation mappers. They use meta classes. They're typically a bit more complexer examples, but they use it. Like SQL Alchemy is using meta classes. Django is using meta classes and places some other tools. And I think you don't necessarily have to use them to write an application, but they can be very interesting to actually look at your code in a programmable way. So I have some examples where you actually look what the code is doing, especially if the code is big and you just got the code from somebody else and you don't know really what's happening. You can read through all the files and grab and use some other static tools, but you could also use meta classes to search for the different things at runtime of the program, and this can be pretty. You can always program it by hand some way, but meta classes might be a very nice tool for this. That's my opinion. Okay, that's maybe sets the pace for meta classes a little bit. And now we have to look at a little bit how they actually work, what they do, to see some examples that you can apply. So the new style class is needed here. So that's Python 2. It's important because in Python 3 there's no old style classes. But you could also define a class instead of saying you inherit from object. You could don't inherit from object, but you can set the meta class. That's the way it works in Python 2. You can set this meta class here, and now I set the type. The type is this built-in standard meta class, and this would have the same effect. And now if you look at this new 2, this gives you the same thing. So typically you don't do this, but you can, because this object inherited from object would have the same effect. And it's typically nicer just working with inheritance from object than just introducing yet another concept of the meta class. Because now every class it inherits from new2 also would be a new type class. That's actually what happens. The object has a meta class type, and then when you inherit from object, then you will get a new style class. That's in Python 2. So there's a few ways to do this, how this works in Python 2. So either you inherit from object, you get a new style class, then you get the meta class from here, or you go to the basis for the classes you inherit from. So you inherit there's every class has this basis attribute, and this is a tuple of your base classes. And in this case, it's just object, a tuple with one element with a trailing comma. And Python's looking there for the meta class. Yeah. So if you don't provide one, then you get it from your parent. Yeah.
Does object have gender meta class?
Object has, good question, I don't know. If object has done the meta class, which is, no, there's no meta class here. Because object is a built-in, and then you inherit from there, you get it, but doesn't have it under meta class. So object is special in many ways because it's a built-in one. You typically just inherit from there. Yeah. Yeah. So that's Python 2. That's the past, but you still, a lot of people use Python 2. You still have to know about this, how the new style business actually comes about. In Python 3, it's a bit different. So in Python 2, the way to define a meta class would be like this. In Python 3, the syntax is different, which is a bit a problem. So if I have a class, then I can define the meta class with this keyword here, and I could use type, which doesn't do anything because it's a meta class anyway. But this would be the way to go, and you have to use this syntax. The other syntax does not work. That's a bit a problem because it makes it very difficult to write single source code for Python 2, Python 3, because you won't even compile, give you a syntax error in the first place. But there's a workaround. I will show you a workaround how to do this. Okay, this is how those meta classes work. We still don't know how they actually implemented and how they work. Hopefully we'll get to this. Because classes can be actually defined dynamically. So instead of saying class C, which inherits from object or not, in Python 2 or 3 is not a problem, to do something like this and setting an attribute in the class. The same thing could be achieved using the built-in type. So you could use type and dynamically create this class. This is always possible. Use type. And now you provide a tuple of the base classes, and you provide a dictionary with this with the attributes. This would be exactly the same. Somewhere closing parentheses. Yeah, this would be exactly the same. So you're not restricted to define classes in your source code file. You can actually define them dynamically at runtime. Typically, you don't do this, but you can. So if you don't know beforehand the name of your class or the attributes, you can do something like this. And of course, you can also implement all the methods like this if you want to. Something like this. So you could write those methods just standalone here. Something like this. So now I define those methods standalone. And now I can actually put them in my class. So the dictionary is not restricted to this one. I can add them to my dictionary. And if I just call them with the same name, there's no difference here. That's pretty fancy. So I just put it like this. So the init and my add method. So I just, of course, makes a lot of sense to give the same name. So if I do something like this, then yeah, sorry, too many. So talking and typing. Okay, now, finally, now you can make an instance of your class if you like to. And the init now takes a value. You have to provide a value. And now, yeah, I have said it, but I didn't type it. So, okay. And finally, now you have this, and now you could look at the value which would be there, and you would have the add method if you want to. So actually, if you want to, you can totally dynamically construct the class at runtime, which you shouldn't do unless it's really necessary, because this makes it much more difficult to read. But sometimes it can be useful, some purpose to construct something at runtime and build a class later on. And that's actually what the meta class is doing. It's building the class for you, and you can work with this. Because you can define your own meta class, so I can define my own meta class, and this is very easy. So the syntax is exactly the same as for normal classes. So if I define my meta class, I just, instead of inherit from object, inherit from type. This is important. Once you see this in your code, somebody defined a new meta class. So if you search for this parentheses, type parentheses in SQL Alchemy, you find several places where they define meta classes. Yeah. It should work with Python too. I did the same thing in Python too. You're sure you have the self here? This should work in Python too also. Are you sure you made an instance? That sounds like you called it in the class. So if you get an unbound arrow, it's typically you call it in the class. Yeah, so if you call it in the class, you have to provide the instance as the first value if you want it. That might be it. So you have to make an instance. Okay, so now as soon as you see this one, then you define a new meta class, and now you can do a few things. In this case, I don't do a lot. The only thing now I override is the str method. So the str, whenever you convert your object to a string, and now instead of writing self, you write class. Of course, you are free to choose whatever you want, but it's highly recommended to use class, because now we're one level higher. So instead of having self for the instance, we have the class, because we build the class. Yeah, this is just my sentence. A meta class is to a class what the class is to an instance. Yeah, so now we put this type here and class there, and now I can just return whatever I like. So I have this example here. Yeah, just say hello for now. So you can just return whatever you like. Now, if I make a new class, so depending on if you're in Python 3, then you say meta class. If you're in Python 2, you have to use an underscore thing. Meta class, my meta, pass. And now if I look at my A, capitalized A, so my class A, then I have to print it, convert it to a string, then it should. Yeah, it gives hello. Compare this to a normal class. If you have a normal class, my class C from before, if I convert it, you would get something like this. This is a standard. And now I overrode it. So I can change the behavior of a class. That's pretty strong, yeah, because people typically expect some standard to happen. Now something changed. So we have to think twice once you do it. But that's pretty much it. So you override, you define a new meta class, which you can now inject this way. If you want to do it in Python 2, you have to. So if you want to do the same thing in Python 2, you have to use a different syntax. You see in a minute how to actually do it. So we have something like this, and if I have my class A, which is supposed to be, so no need for inheriting here, because I said the meta class this way, yeah, and this would be now converting it to a string would give this. So that's Python 2, just different syntax. Yeah.
Question. Just in your my meta there, the string you pass in class in, is that actually a class method, or are you really just passing instance?
Just the instance is a class. So,
Yeah, no, I know.
so because now we're one level higher, and actually the CLS will be a class. This will be my A in this case. In this case, this will be capitalized A. Will be the real class. As opposed to when I define a method in A, that will be the instance itself. That's why you call it C.
Treating class like instance.
Yeah. So because everything you have learned about how classes behave with methods, you can apply the meta classes. The syntax is exactly the same, but I strongly encourage don't use self, use class. Otherwise, you will just get confused. It's too confusing already. So you try to at least get the names straight and use class. Yeah. But exactly, because you get the class. But this is what typical what self is, which is the instance. But now the instance is the class because you're one level higher.
So every class that say is a subclass or whatever inherits from that class is an instance of this.
Yeah. So the type is a built-in. So this one doesn't have to do a lot. Type is a built-in. So everything is an instance of all classes are instances of type. That's why you say type of a class, you get type back. Yeah. Because everything. Yeah, he was first.
But so the meta class doesn't show up in bases though, correct?
No, meta class is not a basis. It's one level higher. Basis is the object would be basis, which has a meta class. So if you don't provide your own meta class, you get the meta class from the parents. You look at your parents and take the meta class from the first parent.
So it inherits meta classes the same way it inherits parent classes.
I didn't understand. What do your question? Yeah. Okay. We have that.
Do you have any idea why they changed or removed the ability to set the meta class by the meta?
Yeah, there's why the change of the syntax. Some people didn't like it. They said this would not be the right way to do it differently. And it was the rationale is probably like this: Python 3 is not backward compatible anyway. That would be the only place to change it. But this is probably the biggest thing because you actually everything else you can work around, but the syntax change you cannot work around. It's pretty strong. Yeah.
So to clear up the gentleman's question, he asked if inheriting from meta class, and that is the wrong thing to think how it works, because you're not actually inheriting from a meta class. You're instantiating a meta class to get a class, and that is what is in the basis.
Yeah. So the question was about inherit. You can inherit from meta class, but you just make a new meta class. Because now, if you inherit from meta class, you're still in the meta class level. So you can do the inheritance works exactly the same. So you can have multiple inheritance if you want to. We have to be careful with multiple inheritance. There are some caveats with meta classes. It doesn't work exactly like classes because you have to have it's a base class kind of thing. But typically, if you inherit from meta class, you don't get the class. You could just get a new meta class, which is a derivative of this original one. And then you can do something. So you can do this. But it's a little bit, there are some, I will show you an example where this can cause a problem. Okay, let's go back to Python 3. And now, actually, I want to show you what you can do here with this class. You see, if I use type of C, which is a normal class, just to see this, you get type. That's everything is like this. If you don't use your own meta class, but if you use a type of my A, which I gave my meta class, I get my meta class as a type. So it's a type, it's a new data type of a class. Yeah.
I figured out what I was trying to say was that if, and I just demonstrated it worked as I expected, if you set the meta class for A, and then you inherit B from A, B dot meta class will be my meta.
Yeah. So the question was if you have a class A that has a meta class and the class B inherits from A, then B has the same meta class as A. Yeah, that's what I said. So if you don't define a meta class, it takes a meta class from the first parent. Yeah, so that's what it's doing. Okay. Typically, what you do very often, you want to do something useful. Now we have this knowledge. We want to do something useful, and typically you override either new or init. So the same thing. Classes have an init, init, but also new. New is rarely overwritten because you don't need it very often. Meta class is a bit different. New is overwritten more frequently. They do very similar things. I just show you, if I define a class, my meta, I can override this inherit from type to make it a meta class. And now I override the new. And the new has a certain signature you have to preserve, new. And now you don't get the class, you get a meta class. So if you define a normal class with new, you don't get self as the first argument, you get class. That's hopefully you know this. And now, one level higher, you get a meta class. The meta class, and then you get a name of the class you want to construct. You haven't constructed the class yet. And you get a tuple of the base classes, and you get a class dictionary with all the methods inside. So, and now I don't do anything else but print out all the things so you can see what's happening here. We don't do anything special yet. But you'll see that you would have the possibility actually to go in here and change something. And now, of course, now you have to call the super class. So since we are in Python 3, you can just say super. That would be fine. In Python 2, you cannot just do it like this. You would have to say my own class, and what is supposed to be self is meta class here. This would be Python 2. In Python 3, you could quit this empty, and then you call the new, and you provide exactly this thing here. So you have to call the new, and you can copy this one. So if I've done everything right, then I could now.
Do you have to supply MCL as well?
Yes.
Or
Yeah, because it's like new, so you have to provide it because you have to actually return. The init you never return anything from the init. It's actually the same for classes. So the new is not special to meta classes. Classes have new. It's rarely used, but they have a new. And in the classes, you get the first argument, the class, and you have to provide it. And now I have to call the super here. And once I do this, now I can make a new class and use it as a meta class here. So again, new, and I'm in Python 3 now. I have to use this syntax. And I can do something. And if I don't do anything, I just define it here like this, then I get something happens. And now it's different. It happens at definition time. So you're much earlier in the process. Typically, you define a class, nothing happens yet. Only when you make an instance, the things start. Here, when you import something, it happens. So people won't, if you do a mistake in a meta class, people won't be able to compile. So this can be a good thing, because if there's something wrong, you won't be able to execute anything because it doesn't compile. That doesn't work. You cannot import it, for instance, if you want to import it. See, now you see we have the meta class here. Then the name is new. That's the name I chose here. And then we get the dictionary. And where's the basis? I've forgotten to print the basis. Yeah, the basis is a tuple with base classes, which in this case is empty. Of course, I don't inherit from object. If I would inherit from object, which I could, that wouldn't change a thing here, then the object would be in there. So, and now, since we are new, you could actually go in and change, for instance, the class dictionary. And this is very powerful, because now you can, at this time, go in and just delete methods, put new methods in. I would be very careful doing this, yeah? But you could. That's a new. The init is very similar, but the init comes later. The new comes first. Actually, we'll look, let's say, later on in Python 3, there's even a prepare, which comes even earlier. But the new is first, and then there's the init. The same thing applies for classes. So the same thing I could have done for a class. The init is interesting, but by the init, you can access all the things, but you cannot change them. That's the difference. So this is, you can pretty much copy this, and now you have the init instead of the new init. And now you don't get the meta class, you get the class. The class exists already. Yeah? So same thing if you have use init in the class, the self is there already. Now the class is there already. So it has no meta class. The rest is the same. And there's no return, but rather a super. So I say super here, no return, but I still have to call super to make everything work. And now in Python 3, I just can keep it empty. In Python 2, you have to put in my meta and class. And class is the self. And then I have to call the init and have to use the same signature. So, and this would look the same here. When I make an instance, so I make the same, I copy my code of the instance here. And this gives me the same printout, only now it's not. What did I do? Ah, yeah, I don't supply the init here. No, there are no init here. Because it's the init now, because the class is there already. Yeah, that's a mistake. That's a difference to new. And you see now, I see it's pretty much the same thing here. I see the meta class, and not the meta class, the class in this case, the class name, the tuple with the parent classes, and my dictionary with all this namespace that's in there. So if I would have defined a method here, yeah, now I'm in a class, now it's called self. Now I have to be very careful if you're in a class or meta class. Typically, you define a meta class once and then you don't touch it anymore, and you only with classes. That shouldn't be difficult. But now you see, now the self method is in there. And I can access it. In the init, you can only read it, you cannot change the dictionary. You can change the dictionary, but it doesn't have any effect. In the new, you can actually change the dictionary of the class. So, yeah.
So the first case where you're calling it's from within under new, does that super call end up resolving to type?
Yeah, actually.
It would be like the equivalent of calling type underneath.
Yeah, this would be type in this case.
And the second case, what is it? It's different again.
Second case is init. This is init.
Does that end up resolving to type under init?
Yeah. Yeah, the super always, in this case, and you put in the meta class, you have to put the class in here. Because the new, if you implement the new in a class, then you would get the class here. So if I have a normal class, typically I have a normal class, no meta class magic in here, class B, which inherits from object. Then I can define an init, as I usually do, and an init takes self and maybe some value. This would be my init. So now I could call super, but you don't have to because init usually doesn't do anything. But you can also have a new here, and this new just takes the class as a first argument, and a few other things I have to check, and then you can override it. The new is rarely implemented in classes, but it exists in classes also. You could also get the basis and stuff. Yeah.
If you don't say that new is a object in Python 3, the object that gets created is still an object, but you don't see object in the basis list there. Is that applied at some other point?
You don't see basis, you have object here. If you put object there, you should see it.
Prove that it's not showing up for me in the printout.
Here? You have to put basis here.
Right, no. If new does not explicitly derive from object,
Yeah, then it doesn't show up.
but it does actually get applied to the object.
Yeah, you have it's not in the basis, but the behavior is not different because you provide the meta classes, but still the basis is empty. Because that's what happens. There's no basis. The same thing in this Python 3, Python 2 should be the same. Yeah, because now you get the meta class explicitly. You don't need the meta class from object because you have meta class already, so it doesn't look at the meta class from object, which is the only thing that would happen here. Yeah. Yeah, in Python 3, you don't have to do anything. You don't have any special any meta class, no object. You still get a new style class. Yeah. So my purpose is here. The new is not specific to meta classes. It can be used in normal classes. There's no specific thing there. But it's way more frequently used in meta classes because it gives you more power to change things. In classes, usually don't need it too much. Because if you have init, there's an instance already here. Yeah, there's a self. Whereas if you use new, there's a class. And I don't remember the signature right now. But there's I think, basis and name basis. Like this. Yeah. So and here you have to say return new, return super. So in Python 3, I can keep it empty, new, and provide the same thing. Also cdict, yeah. So I hope it works. So then if you have something like this, yes, now I can make an instance of B, and hopefully it works. Yeah. So it's not used that often. Yeah. cdict is not there. They're required. No, it's a normal class. I just can use it like this. That should work for now. Yeah, and I have to put the value. And now I have the value, I have to put the value through also. Because I have this, the value goes through here, and this would be the value. If I do something with it or not, doesn't matter. I put value, that should work. Yeah. So it's a bit, new is very rarely used. So you usually don't remember actually, because it's a rare thing. In meta classes, it's more common because it gives you more leverage what to do. So I would recommend, if you just want to get some information out, use init. You don't get into the trouble to change things by accident. If you want to change something, use new. So that's typically what I want to do. Okay. One more thing about Python 2 and Python 3. We saw this. I will have to switch back between Python 2 is like this and Python 3 is like this. But there's some clever hack here you can use that actually if you go to meta classes, see you have quite a few examples. We want to show you a few things. No, go up and in solutions. And in solutions. And if you look at meta classes, you see quite a few. And one of them is meta 2, 3. So this is a clever hack. So you don't have to understand actually everything. But if you use it, then you have one syntax that makes it work with Python 2 and Python 3. So you see, this is it's not from me. It's from the Jinja project. And this has quite a few explanations. I put it in here. That's from this source here, so you can, if you want, you can read through. And they do some fancy things. Actually, they replace meta class with itself somehow. Yeah. So you have this meta class. You get a meta and return a new meta. And this has a few advantages because you kind of create a temporary stuff in between and do a few magic things. Yeah. So you define a new meta class, which you actually return here. Yeah. And there's a call is the one that is used when it's actually created, and the init, you have to replace it. And you see here, you override the new and return this meta here at this place. So this is something kind of magic, it works, but once you import this, then you can use the same syntax for Python 2 and Python 3. Yeah, so once you have it, see now I have this one, and now you can run this meta class, and you supply the meta class and potentially the base classes if you want to here as arguments, and then this would work with Python 2 and Python 3 without problems, which is otherwise not possible because you would have a syntax error. Yeah. So this is just, so you don't have to get deep into here, but now it works with here. And if I copy the same thing over here and do it in Python 2, exactly the same thing, and run it with Python 2. You see now it works with Python 2. So I just get and print out the version I am. And it works with PyPy also. I tried with PyPy. I haven't tried with JSON, but it should work. Otherwise JSON would be broken. Yeah, hopefully. Yeah, so it works with PyPy, and PyPy2 and PyPy for Python 2 and Python 3 PyPy works. Good. Now, let's look at some examples. So now we have this potential, this powerful thing to override new in init, and I have one example here that goes in the direction checking your code, kind of restricting what you can do with your code. And I have this example automator. No class attributes is called. No class attributes. Okay, so my use case is as follows. I would like that it's checked that no class has anything else but methods. No non-callable callable attributes should be allowed. So a class can have a method 1, 2, 3, 4, 5, but the class shouldn't have like x equals 10. That's my use case. And this can be checked automatically. So I don't know, it's just I made it up, but you can use the same principle for any kind of use case. You want to check something on the class, that your class, maybe if you have write a framework and your user has to write the class, then you want to check that the class has some certain kind of behavioral properties in a certain way you wanted to use. And if something goes wrong, your exception say something wrong with the class, fix your class. Otherwise, it's not going to work. Maybe. Something like this. Or in this case, I just want to parent these callable ones. So there's a few ones that I want to allow. So I define a new meta class which is called no class attributes, because non-callable class attributes. And now in this case, it's enough to override the init because I don't actually change anything. I just want to check how things are. And if something's wrong, I just raise an exception. So there's no need to override the new. You could, but I decided to use the init here. So I just have a list of a few things I would like to allow. This is a list, actually a mix up between Python 2 and Python 3. The qual name down here is something special to Python 3, and the meta class special to Python 2. But it doesn't matter, because this is just a positive list what is allowed and not required. So it's no problem to have more. Because I want to allow these. So if you have something strange, you can add another name here. And then the only thing, all the action happens here. I get a dictionary, just a normal dictionary, which contains everything that's in the class, and you just go through, and I get all the names and the values. And then the only thing I need to check, if here, I just put this down here, this end, and so now it's not correct syntax anymore. Just if I put the parentheses, it is. Yeah. So I have a few more parentheses that are necessary, but to make it clearer. So I check if the key is not in allowed. So if it's allowed, nothing happens. But if it's not in allowed, and if it's not callable, that's my two conditions. So if something like x equals 10, then I say I don't like it, just throw an exception. That's all that happens here. And that's it. Nobody can ever define a class like this if it's a meta class. Otherwise, I just use super and do it, and everything's fine. Yeah? So now you can run this, and it should run in Python 2 and 3 because I use this Python 2.3 thing here. And you see, now you could use meta class in every class, but the easier thing is just define one class that has a meta class, or the others just inherit. Yes? Yeah, so the question was about what happens at runtime. Yes, that only happens at creation time when I actually write it down in my file. If somebody dynamically later on adds something, I cannot check here because it's a new, or the init, that was only called when I use the parentheses and actually do it. If somebody after the class is defined dynamically adds something, which is possible, no problem, then I don't check this. You would need other strategy. As like, there might be some way to do it, but not this with this method. Yes.
Use the meta class to add the set adder into the class.
Yes. Now if you override a new, you have this dictionary and you can replace anything in the dictionary. Yeah, so you can do, so if you have this, you could put the get attribute in there, and then you have full control what happens. That would be possible. Yeah. But not in the new directly, but indirectly overriding get attribute, which just would allow certain attributes, setting new attributes wouldn't be allowed. If they're not there already, just you would wouldn't allow. Or get utter would be enough because the checks is not there. Okay, now you see, though you don't have to do this with metaclass, you have to do it only once, and now you just inherit. So you can avoid this thing, and then you just inherit here. So actually, you could isolate this. There would be a way to isolate the Python 2 and 3 specific stuff in one module, just import it depending on Python 2 and Python 3, which also would be possible. Getting around the syntax error if I wouldn't have this nice trick. Because then I just inherit from it, and I would get the meta class. And this is fine, because I only have method, and nothing happens here. But the next example, this is not allowed because A is not callable, and this will throw an exception, because I throw an exception. And this happens at definition time. So for some reason, I can now, you see the first one works, hello from attributeless, and the second one gives me this exception. It's exactly my exception. I just throw and say, okay, found non-callable class attribute A. Yeah? So you can do something like this. So you can have all the powers to look inside what happens in the class and say, okay, this is allowed, this isn't allowed, for instance. This would be something. So if you need it for your framework and you say, okay, these methods have to be there, this shouldn't be there, and this type of thing should happen, this should not happen, you can do this here. And even the init is enough. If you just want to check something, init is enough. If you want to change something, you need to do something more complicated. Good. That's this. Are you familiar with decorators? So there are decorators, and there are also class decorators. So some of the stuff you're doing here, you can actually do with a class decorator. Yeah? The class decorator is newer than meta classes, actually. So you could actually get a similar effect here using a class decorator. So I load this here. Since there's a bit more, I don't want to type all the things. Load class decorator. And I get the same effect with a class decorator. So a class decorator is just a decorator. Maybe I show a class decorator for simplicity. I just define a decorator that takes a class and is doing something with the class. And I can say class attribute equals 10. Return class. That's it. So I get the class do something with the class and return it. So now if I use this decorator, just like a normal decorator, so you can call it whatever you like, show the decorator, define a class, and the class doesn't do anything. But now if I look at my class, it has an attribute, which is 10. Because at this moment, when I define this here, and I execute my cell, then this object A will be put in here, which is a class, and I see this one. So you can just visualize it just by printing the class. And you will see, if I run this again, it prints a class at definition time. That's what the class decorator is doing. Yes?
Basically, you're decorating the vendor new for the class.
No. There's no new here anymore. The class already exists.
So what function are you decorating in the class different?
The class itself. So I get a class object, and now I can do everything I would. This would be the same thing as saying a attribute 2 equals 100. So if I do it later on, but I don't have to actually write it, I just put a decorator, and I can reuse a decorator for many places. So you could always do it later. Yeah.
So in this case, excuse me, the decorator happens at runtime, whereas the
No, it happens as soon as I execute it, if I define it, and I import it. Yeah? Because as soon as a class is defined, if the class is the module level, yeah? As soon as you import the module, the decorator will be run, just like a normal decorator is. Yeah? This would be the same as defining the class. So this would be the same here. This would be the same. Yeah? This would do the same thing. So if I don't apply the decorators, it would do the same thing. But I don't have to do it because I can, if I want to use a decorator for 10 classes, I would write the same thing for 10 classes, decorator write it once. The decorator is there, the class already exists, so there's no new, but it's after the init, and you can do something. So you can get the same effect with a class decorator. See, I used, this body is pretty much the same thing as I did in my init, just checking for this thing. So actually I could have refactored out in one function, but here I have a few more things because now I have, all of a sudden, the weak ref also and the dict also appears here because I'm later in the game. Yeah, but it doesn't matter too much. But I can still go to the dictionary and throw my exception. And this works, and I'll just put this decorator here in front of it, and this will be fine, and this is exactly the same example, and this won't like it. So to a certain degree, you can replace what you used to do with metaclasses with class decorators. Yeah, but you later, you see, that also that's why I need to put more in here, because there's more in the dict already. But if you only want to check for certain types of things, for like checking that some certain things are in the class or not, then this class decorator thing might be okay. Yeah, you see now down here you get the same effect, the same exception as we had. So this is totally equivalent to the other one with the meta class. Here. Good. But there are some examples where this doesn't work. And next is the next example. And this can be interesting, maybe. So I just load the slotted types. So I have an example which is a bit bigger, and this one actually uses a descriptor along with a meta class. So of course we know it's a descriptor, so we can use it. And this one dynamically sets slots. Are you familiar with slots? So slots is actually a feature that's mainly there to save memory, because if you make a lot of instances, every instance has a dictionary, carrying a dictionary around. And dictionaries take quite a bit of space. There's a lot of empty space in there. And if you make millions and millions of instances, then you might, when you want to save memory, you might consider slots. And slots are very easy. Slots, you just specify the names of attributes you want to set, and then you won't create a dictionary. This saves space. With the side effect that only these names can be set, nothing else. Yeah? So if you have this slots, so if I have a class, maybe I'll show you an example first. Class S with slots which can inherit from object. Yeah, and I set the slots property, slots. So now I say slots is a list of names, and I only allow A and B. Should be strings, A and B. Then slots, must I write it right? Yeah, and now if I make an instance of my class, then I can do something like this. This would work, yeah. But if I want to do something like this, it doesn't work. Yeah, it doesn't allow me to add attributes at runtime, which I usually can with normal classes. That's a side effect. Because it's not stored in dictionary, there's also no dict, because you have the slots here, and you only have the names. Of course, in the init you can give this initial names and stuff like this. That's what slots are doing. So if you run a slots, and the problem is slots are very early in the process, so they're before the init, so you have to use a new in your meta class to actually get to the slots, because that happens earlier. So it's always the question when things happen. So, and that's what I'm doing now. I have here a descriptor that helps me to check types, type descriptor. And you see, because now I have a descriptor and I supply a data type I want to check. So there's another example for descriptor. I want to check a certain data type. And if there's a default value, I set a default value. Otherwise, I just create a data type. So a data type can be something like int. Yeah, int can be a data type. And if you call int like this, you get back a 0. It's like when you call list, you get back a list, and so on. List, int, float can be data types. So I want to create a descriptor that checks that some value has a certain data type. And here, the get is easy. I just return from the name from the instance. So I say instance.name. The get attribute is doing nothing else but saying .name. And if it doesn't exist, I return the default value. But setting. So I check that the value I get is of this data type. If it's not of this data type, I throw an exception. Yeah, I just give an exception here that tells you that that's not going to work. Otherwise, I just say instance.name equals value. That's what set attribute is doing here. I cannot say instance.name because I don't know the name. I get the name as a string, and I use a set attribute. And I override the delete. So this is a descriptor that does a little bit more, but it's checking types. And now I have a meta class that actually is enforcing this because I want to get in before these slots here. You see, I make a new list of slots, and I go through my dictionary here, and I check if it's a type descriptor up here. Yeah, I'm missing the E here, but it doesn't matter. The type descriptor. And then I use 2 underscores and save it as a secret name. This is a name here. I could to all my slots I have here, and just append this value name here to my slots, and then I can set the slots. So I have hidden the value with a key, and then I have my slots, and then I have to do the super here. So once we survive this, we can use it. And the usage is much easier. So the definition is very complicated, but the usage is pretty easy. So now I have here attribute 1, attribute 2. This should be an int without default value. It should be a float with a default of 5.5. And then, since I use slots, I create new slots. Only attribute 1 and only attribute 2 is allowed. And you can see this. I make an instance of this class, and I show you the 2 attributes and everything that's in my instance. And you can look at the slots. And I can set my attribute, which works. But setting an unknown, it's not going to work because I have slots. So this is, I could have the same behavior just defining my slots here by hand, but I would need to repeat attribute 1, attribute 2 is in the slot here. And I don't have to do this, it will be done automatically. So attribute 1 and attribute 2 will be done as a slot. And once I do this, you see, now I can set this. I see a few things. These are these names in here I set in the dir with the underscores, actually. And then it's not allowed because this has to be int, and I got the float. Yeah, that is this one here. At this place, because this is supposed to be an int and not a float. When I make it an integer, it works. But I get a next exception down here, and it says my class object has no attribute. This is not allowed because I cannot set this unknown. Is this there? Yeah. I get an exception. So this is something I could achieve without using a meta class, but I would need to have a repeat. If I don't use a meta class, I would need to have done something like this. Yeah. So I can achieve the same thing without a meta class, still using descriptor. So I just inherit from object. But to get the slot thing, I would need to repeat and say slots equals, and now I have to use the strings, exactly the same name, attribute 1 and attribute 2 to forbid to make it slots. Yeah. So you have to do something like this. And then, but now you see this boilerplate. Oh. Yeah, I cannot set it here. I'm too late, so it doesn't even work. My nice example. Yeah. Yeah, so it's not that easy as I thought. Okay, now we'll do a live demo. Now it's the same thing, has nothing with the descriptor, so I cannot even set it here, the slots, because it conflicts with the class variable. Because the slots cannot be used for classes, they now have to use I have to give up my whole concept of, actually the slots are underscored, sorry. You see I use the underscores in the slots to hide these names. Now it works. This would be the same thing But I would need to repeat this here. I would need to exactly have to make this name with 2 underscores into slots. In the meta class, I don't have to worry with slots. I don't have to know that slots are there. I hide this complexity a little bit. I still have to do this checking, and the meta class is pretty complicated here because see, I have to do this. Yeah, because I have to append this to the slots and allow this one, and the other one are descriptors. But then the usage gets easier because I don't have to repeat the slots with the underscores. Yeah. So that's one example here where you can simplify code, and you don't have to. Otherwise, you have to tell the people always add this line here with exactly the names. If somebody mistypes something, if you mistype something like this, it's not going to work. Yeah, because then we'll find the name. Yeah.
When you're using slots, since that class doesn't have a dict, how can you interactively introspect what variables an instance has? If you do vars in an instance, it goes up.
Yeah. So you have my class up here. If I make an instance of the class, then of course I have slots. So there's no dict here. There's no dict, but there's slots, and then I know the names of those slots and can access them. So they can be accessed now. Yeah, this is for the instance, and not the method. So now I can access. Doesn't it work? Oops. I cannot access them like this because I use I made a mistake. I have to execute this. Probably a mistake here. I messed around too much, is it? Okay, this works. Yeah, so I can access the instance here, and because now you have slots. The thing is, if you want to get into slots, you have to use a new. Otherwise, you won't be able to do it. Yeah. So it takes you a while to write those things. It takes you a while to debug it. But then, if you, instead of repeating this maybe 10 or 20 times, you don't have to repeat this. This will be done automatically for you. Yeah, that's what this new is doing here at this place. Yeah. So if it is setting this for this type descriptors, just adding this to the slots, and you don't have to do it by hand. But if you try this in the init, it's not going to work because you need a new to do this. Yeah. Yeah, I want to hide them. I don't want them to be accessible from outside because they're just I use two descriptors, but they should have. I use a different strategy here. You could have used my weak key thing to do it, but here I stored an instance. I used 2 underscores actually to store the value in the slots. Yeah. Yeah. The descriptor is just accessing the slot with the 2 underscores at this place. Yeah. Yeah.
I'm missing something. What is actually tying the underscore name to the original name? That's what I was trying to find out. Like, does Python know that all the slots are named double underscore the other thing? The get on the type descriptor doesn't use the double underscores.
You asked for the name. And you have the
You're creating 2 slots named double underscore attrib1 and attrib2. But then you use 2 other things called attrib1 and attrib2 without the double underscore. Is it using those slots somehow?
so this what I'm creating here. These are instances of my type descriptor. Attribute 1 and attribute 2. When I say attribute 1, I go to the type descriptor at this place. Yeah, I go to the type descriptor, and the type descriptor at this place when I say get, I get the instance and the class, and then I say self name, and the name I'm setting here at the beginning, which is none. And where do I set the name? And here I set value name. That's where the connection comes from. So I set the name there, and I append the name. The name is twice. So here, this is a value dot name, which will be used in the descriptor, and this is a name that I append to the list slots up here. And there's a connection. There's two. Yeah. So value dot name. The value here is it's what's in here. Yeah, and has a name. Yeah, and here I get, you see the name is none of the descriptor, but here I say self name. Yeah, so I said this because I check here if this value is the instance of a descriptor. So this value is the instance of the descriptor, and then I set the name of this attribute as a descriptor. Yeah.
Okay, so what it's protecting is that you can't overwrite the type descriptor.
Yeah. So it's actually it's
Self.something.attribute1
yeah.
equals 10.
Yeah.
It won't let you because
It's doing two things. First, it only allows me to have two attribute 1 and attribute 2. There's nothing else. So that's the first thing. So because it's slots, there's nothing else to be said. And the second one is it checks for the type because it's a type checking. So two checks. So I restrict my instance to this named attributes. There cannot be any new ones. And in addition, I check the type. It's a type check. So two checks. Would that work? You mean it here? Scroll down. This one. So this one, if either this would fail because it's the wrong data type, and if this is the right data type, then this would fail because it's an unknown because I use slots. That's the two effects I have here. Yeah. So I have a pretty restricted thing here, which first is typed, and secondly, only these two attributes are allowed. If I say add another attribute here, that would be allowed, but nothing else would be allowed later on. This could be useful if you really want to prevent setting things later, because for some reason you don't want anybody to, by accident, add anything to your class. This would not be possible here. Not as an instance. Instance is a different thing, but class. Of course, we have the class here. No, instance also, sorry. And then there's the instance, because you don't want this. Because as soon as you go to the slots only allow these two names, and these type descriptors allow this one. Yeah, you can still set the slots directly, but that's why you have to underscore, so they are not by accident. Nobody's going to set them. Yeah.
In this case, the point of using slots is only perhaps to protect your instances of this class from being polluted. It's not so much for the memory saving.
Yeah, in this case, it's recommended to use it only for memory saving, but sometimes you might want to protect your class from if you want to have a special need for your class, like if you want to create a table out of write somewhere, you don't have any extra in there, for instance. Yeah.
So, like in this case, you're basically you're creating all these descriptor classes and all this other stuff, which is actually going to consume probably more resources than just having the dict.
Yeah. So. Yeah. So it's not about memory saving. Yeah, the point is the question was about the memory thing. Of course, you have the descriptor. Descriptor also needs memory. Yeah. But the descriptors there's only two descriptors in the class. If you make a lot of instances, there won't be any new descriptors. So it's just for the class. If you make 1 million instances, you won't have 1 million descriptors because they always share this descriptor. So and the value is stored in the slot in the class. So it should be okay. Yeah. So. If you want to be serious, you can measure some memory. So the other tutorial, there are some tools. The tutorials I gave with other PyCons before to measure memory, you can see actually what really happens. It can be interesting. Okay. Any more questions? let's continue. I have another use case. Well, hopefully that is a little bit useful. I have two more use cases here that might be interesting because I tried to use meta classes actually to count how many classes are defined in my. It's like use case. I get a new big code base and want to investigate what's going on. How many classes are actually defined in there? Really defined. I get really imported. What's happening? And I have a version that works with Python 2 to some degree, and have a version that works with only Python 3, but it's better because Python 3 adds something new. So let's look at I'm a Python 2 now, and I call this. No, I'm not here yet. Autometa Python 2. So this is an automatic kind of meta class I want to inject to get a certain behavior. It's not that long, actually. So I have a meta class which inherits from type, and this meta, the task of this meta class is just to count how many classes actually get defined in my code. Not instances, classes. We are not instances yet. How many classes actually, when I import, how many actually after are in there. And this is pretty easy. I only need to override the init because I just need to count. I don't want to change anything. And then I don't want to count myself. That's why I set a counter to -1 here. And I increment the counter. Every time the init gets called, I increment the counter. And I use the bug meta counter here to increment the counter. Sorry. And then I also append the names. I see which names are there. So you could do something else. This is just bookkeeping what classes are actually defined. And I have a report method which just gives you the counter and the names. So what I gathered here. So far, they're good. But now what I'm doing, actually, I create a new object which inherits from object, which has this meta class. This is Python 2 syntax. And then I override built-in object. So you have to be careful with this. So it works to a certain degree, we'll see. Not always. It's just, this is for debugging. Don't use this in production code. But it can be interesting because I override object, and object has a different meta class here. So that's what I tried. And actually, I did this, and it works. So I go to the terminal, actually, and run it from the terminal, which I don't want to pollute my my notebook. So that's Python. If I run it from Python 2, so I have a one that it's actually using it. So I can load it, but I cannot run it. Use autom Python 2. So if I load it, it's fine. So that's what I'm doing now. I'm just import. That's how you use it. You just need to import in this function set new meta and call it to get it started. And then I just define a bunch of classes and see what happens. I have one without object. This doesn't work because it's not a style class in Python 2. And once I do this, so it's Python 2, Python. Yeah, you see now I get a list of these classes that are defined. I define 2 classes, and I get the names of these classes printed out. Yeah.
So if you were to run that in the Python console, you could run use set new object and then run some module.
Yeah, import some module.
Without actually having that in the module itself.
Yeah. So now you can use have a different one, a different example. Yeah, the problem one. So I have this. So I take this away here because this is a bit. I don't want to execute it here because I changed the whole setting, and I might lose my notebook here a little bit. I have a problem with this problem. It looks like this. You see now I set it, and I import a bunch of modules from the standard library. That's fine. This works. But as soon as you import one of these, matplotlib, numpy, sklearchy, they use meta classes themselves, and it doesn't work with my approach because they don't like it. I show you the reason. So if I do this now, I have way more. That's all standard library. They all seem to, at least I can import them. So if I do this with Python 2, is there a problem? Yeah. Problem, you see now I get a lot of 6 to 8 classes defined in there because they're all then I get them, it's fine. But as soon as it uncomment matplotlib or stuff like this, you get an error message because that's a problem because now I inject my meta class in there, which inherits from type. And the other meta class also inherits from type, and this doesn't work. I would have to make either my meta class inherit from the meta class they use, or I have to inherit, or they have to make them inherit from me, which I tried, which it didn't work. So that's a problem with inheritance, which is a bit different than normal classes. So if you just change this, uncomment this here, and import, you will see that the error message there. Then it does not work. So it's not that good. But there's a solution in Python 3 actually. Python 3, I have a solution for this, and the Python 3 offers some new method, which actually allows me to, I have it here, allows me to, oh yeah, I have this. Also the base conflict, so I can show you the base conflict first. I go to Python 2 again and load the base conflict, which shows this problem. So to make it clear, that's what I want to show you, base conflict. So if I have something like this, so we have a meta class that inherits from type, and another meta class inherits from type. And now I use a syntax which is the same problem for Python 2 and Python 3 actually. And then I have, and this class has this meta class, and this class has meta class, and then you have multiple inheritance here. It doesn't work. This doesn't work. If you run this one, I can run it from here actually. There's no problem because I don't override anything. Then you get this message here calling meta class basis conflict. Meta class of derived class must be a non-strict subclass. So essentially it means this does not work. I cannot have it like this. If I have multiple inheritance, which is not uncommon in bigger projects, then this is not going to work. This is not going to work. I cannot do like this. So I have to do something like this. This would work if I do submeta. This would be the solution to it. So if I do something like this, see, this one is a meta class, and this one inherits from the meta class, and then it works. Because everything has one single parent. Here, goes back to the single parent, and it works. So now if I do this, this is exactly the same. Now I can do multiple inheritance, it works. So if you do this, it executes without a problem. Doesn't do anything, but we can, because everything happens at definition time anyway here. Yeah. So this works if you have only one. If you have two, then it doesn't work because you have it here and you have two different meta classes, and these classes have different meta classes, and it doesn't work because they don't inherit from each other. And that's a problem I run into at several places. But I have a solution in Python 3. And I wrote a class watcher, which is pretty nice. It works pretty well. Class watcher, which is doing this. So this is a bit longer. The biggest one is just the reporting, just showing the results. So I'm just define a new exception here, multiple inheritance error. And here I have a class watcher. And it's a bit too big, everything. And this is just an object in this case. There's no meta class. I don't need a meta class because I have a different solution. But it overrides a new. You see, I have a class, and I have here I can filter what packages actually I want to check. This is something additional. We can skip it for now because I don't want to just record every class, but I can have a filter, a positive and negative list what classes I actually want. That's some additional thing. And here, you see, I can only make another instance. For that, I thought it would be safer to have only one instance, so I just mark when I make an instance that an instance exists here, and if it exists, I throw an exception, multiple instance error. And then I have defined classes. It's a counter. So I use counter from the collections counter. So it's a special kind of object that you just add things, and it counts how many occurrences you have of a class, because classes can be defined multiple times, as you can see. So I have a counter, and here I activate these packages. This is filtering. Just skip this for now. The filtering with only packages and ignore packages, and I call my super. And then I have this build class. Python 3 provides a new method build class, and I override it as a function. That's why I use static method here. And the build class takes a function, a name, basis, and metaclasses. Metaclass, which is type. And I don't do anything special down here. I just return the original build class, which I save somewhere here. Where is it? The original. In the init, I must have saved the build class. The original build class, which is the built-in one. No, where is it? Later on, yeah, when I activate it. So the activate actually sets the built-in build class is a function that will be called that actually builds the classes. And I'm overriding this one. I replace it with my own version, which is not really changing things how classes are created, but it gets information where classes are created. Yeah. So this whole thing here is just this whole thing is not important. So what is just the filtering of the names, what class actually I want to watch or not. And then, if I want it, I just add this to this dictionary. You see, define classes is a dictionary here, plus this counter, plus equal 1. And then I just build my original class. And I have an active, I can turn it on and turn it off. When I turn it on, I replace the original one with a, I save the original built-in one to the original one and replace the built-in one with mine. And deactivate, I do the opposite. I put it back. Yeah, and this is just a report. It just prints out the result. It's not so important here. But now I can call this with Python 3. So if I call this with Python 3, and I'll show you first what it does, and we can look through again. Yeah, space here. Python 3. And doesn't do anything. Why not? Ah, yeah, I have other one, use class watcher actually. This is just the watcher. Load. Use class watcher. So use class watcher is this one, and this is now the usage is easy. This is pretty complicated, but the usage is easy. You just make an instance, and the instance will activate, and you can activate and deactivate later if you like, and then you write a report. And now I import a bunch of stuff, including Matplotlib, Pandas, SciPy, Alchemy, those problem ones. And once I do this, here I say Python 3 use class watcher, and then yeah, I have to activate. I haven't also installed everything in this environment. Yeah. So this one, of course, requires that you have those things installed. And now I just use Python, not Python 3, because I have environment for Python 3. And it takes a while. And now see, I get a report, and it reports that total defined classes are 1,566. So it's quite a few. And this is listing me according to some of them are defined several times, obviously, because I counted them. And you see where they come from. I have the full name, and you can see here where they come from. And then I skipped because I don't want to have the long printout. You can change the number, how many. You can say instead of 20, you can say 200, it prints 200. Now this one actually gets all this, the classes that are defined, and you can also filter. So if you don't want them, you can have this exclude include list. It starts with something. So if I don't want SQL Alchemy, I could filter this out, for instance, and then the SQL Alchemy wouldn't be there and things like this. Yeah, and this one is not a big deal because it doesn't override object. It just overrides this function, and then you can get an overview about what class is actually defined. So you can experiment with this. That might be useful to work with it. So it's pretty long, and this is here the filtering. So you can provide a list of up here. you can provide a list of only packages you want. So starting with with a name of the package dot subpackage and so on, and we'll take only those ones that match this pattern in the beginning. It's very simple pattern matching. You could make it more sophisticated, or ignore several packages, so it's a blacklist. So you can ignore some of them, and you won't see what's in there. So if you do this, so I wrote this here, you can set it on, and you can also activate and deactivate. So if you do the init, it automatically calls activate here, so it will be turned on when you make an instance. But you could also turn it off, deactivate, and turn it on later on. So not for everything, only for a certain part of your program, between some imports if you want to. And it gives you a live image what classes are actually defined when you import things. So, and this is the only thing that you have to do. You have to have this build class, which is built in here. This is this build class, and you replace it by this one. This one. And the usage is easy. You see this. The most logic is here about filtering the names, and then you only need to increment your watcher and add it to this class, to this counter here. And then you see this. Actually, these 2 lines do all the work down here. That's all you need. The rest is just filtering names for stuff you want. It has nothing to do actually with the logic here. And these 2 lines is doing the counting, and that makes it pretty stable. So I try to, if you fiddle around with metaclasses, you always get into problems with this multiple inheritance. If you do this, you can avoid this. Yeah, so it's not strictly metaclasses anymore, but it goes in a similar direction because you override this build class, and you get some information about what's going on in your code. And I think this can be really useful to get some impression. Good. One more thing I would like to show. The next one is a Python 3 specific thing, and this is a prepare method. The prepare method is interesting because it becomes even earlier than the new and allows you to do a few more things. And I have an example here. Prepare, it's called. The prepare method. Yeah. So this prepares Python 3 only. It doesn't exist in Python 2. And the thing is, I show you here, you can implement, that's a meta class again, and you can implement the prepare. You see, I have a prepare, I have a new, and I have an init here. Yeah. I need to implement all of them here because I define some extra arguments here, and when I have extra arguments prepare, I need to have the same extra arguments in new and in init. That's why I have all of them. And actually, the init is doing nothing else but returning a dictionary kind of object, and this dictionary object is doing something special later on. So I have this dictionary object here, and this dictionary object here inherits from dictionary. So it's a dictionary, and the only thing I override is set item. You see the set item, and if somebody is calling set item on this dictionary, I do a few things, and I can now here at this place have an ordered member list. You see, I have member ordered, and the purpose. Maybe I start with the purpose first. We start with the purpose first, what it's good for, and you see what's going on. Otherwise, it's getting a little bit too complicated. The purpose, I want to keep the order of this, how the things are defined. Typically, everything is stored in a dictionary, so I don't know anymore if attribute 1 was defined before attribute 2 or 3 or method 1 or method 2, because as soon as it ends up in dictionary, I lose the order. Yeah, that's a problem with this approach. Even in new, you get a dictionary, and it's too late. Prepare is earlier. So prepare will actually replace this built-in dictionary here. And then when I do this, I can print out the member order. You see, this is an example here. And now I have this order of the members, and this preserves the order I use actually when I define it. Because prepare replaces for a short while this dictionary this class dictionary with my own dictionary, which actually it's checking in which order those things are defined. And that's what prepare is doing. So you have the meta class here. That's Python 3 only. That's why you can use the syntax. Meta class ordered meta. And once I have this one, now I have this extra attribute, member order, and it preserves the member order. This can be useful if you want to use your class and say, okay, I want to preserve this. My user defines those attributes, but I want to know in which order he or she defines the attributes. Yeah. And for this one, you can do this kind of little bigger meta class here. And you need to have prepare, because when you use new, it's too late because you're in a dictionary already. And dictionary does have a new order. So you need to do this. And the main thing is this prepare here returns this new dictionary I want to use. Yeah. And this is a new dictionary. And this new dictionary has a list of this order here. There's a few options here I have here. And then if I want it, if it's not one that I want to skip, because I don't want to underscore methods and stuff like this. This is just filtering. This is the important thing. If I want it, I just append this this name, this key here, to this order list, and actually call set item of the dictionary. Yeah, there's a dictionary, because I inherit from dictionary. That's what I need to do. I need to override this with a new object that behaves like a dictionary. And then you see here, I do this, and then here I replace. I have to do this extra step. I have to replace the class member order with its cdict member order, because here in my prepare, I can only have this attribute thing, and I can only edit slowly. I can only write it here. I say self member order, which would be the cdict. Self is the cdict in this case. And here I have to take it out because I get it from cdict. And I put it as a class so I can access it later, because the cdict wouldn't be, shouldn't be available. You shouldn't use the cdict directly. So it just said this one. And I can even have a close here. So when I have a closed, then I won't use it later on. Do I need to close somewhere? Maybe it's not necessary. Okay, but that's the main thing of the prepare. So with the prepare, you are earlier, and you can do things you couldn't do with the new. And keeping the order of these attributes can be useful. Like if your class represents some kind of table or something, you want to keep the order of the columns. Then it would be that you would have to have a second line with the order somewhere or something. Because yeah.
I'm just trying to think, could you use like the collections order dict and like replace the class dictionary or something like that?
I just tried that. It didn't work.
Yeah, I'm just trying to think of like
Yeah, there's some black magic that doesn't allow it. So just using the order dict sounds tempting, but I'm not sure why it's not going to work. But the build class, the prepare here, the prepare allows you to get in first. And you can do other things in the prepare. So you can go in before actually the class dictionary exists and could do other things. That's the most common one to preserve the order, but you could also do other things before the dictionary gets created if there's something you want to do before there.
It doesn't fail. It just doesn't order.
it's still an order dict?
When I print out the actual
Yeah.
dictionary at the end there, it instead of member order, I printed out the dict, and it was a regular dict instead of an order dict.
So it's replaced with something.
At some point.
Good. Okay, I think we're up. The time is up, isn't it? Yeah. So we have to stop here. I still have two exercises that would be interesting. Maybe I read it to you, and because I give you the solution. So writing a meta class, then two things: preventing method names that are longer than 30 characters. So something you check. So some kind of pilint, but dynamic, and you can enforce it actually. Or the other one is you want to require doc strings that have at least 5 characters. So something. So your code wouldn't compile if a doc string doesn't have 5 characters, something like this. You can put it in. It's not very difficult. And it might be actually useful if you want to check a code base and you have some regulations, you can force the user to do it. If it's a good idea, it's up to you, but it's possible to do it with a meta class, and you can do something. It's not very difficult. You could actually use my no class attribute example and adapt it. and can do it. Unfortunately, I talked a bit too long, so we don't have time. So I encourage you to do the exercises, and I upload the solutions. And do I have a last slide? Yeah, thanks. So if you want to, you can also reach me. So I will be here the whole conference, also including the sprints. So if you want to, you can reach me and talk to me if there's something. I'm always welcome suggestions to improve or have questions. And also have a booth. So I have a booth 316. So if you want to get me, either write me email or Twitter me or something, or come to the booth. I will be there doing the breaks most of the time. Then you can ask questions. So I hope you got something out of this topic, which is something a little bit esoteric, so, admittedly. But there might be some examples you can apply, and even if you apply them as a recipe, but I hope you understand a little bit of the background, which is always helpful, as opposed to just Stack Overflow recipe application, to get something out. Thank you very much, and I wish you a very nice conference, and maybe see you next year.